right? Now, let's see abnormal molar masses. You know that the four colligative properties were lowering of vapor pressure. There was the elevation in boiling point, freezing point, depression in freezing point, and there was osmotic pressure. So we did the four colligative properties, and in those four colligative properties we were what, figuring out the molecular mass or the molar mass of the solute. Can you please mute yourselves, guys? So there was depression in freezing point, there was elevation of boiling point, there was lowering of vapor pressure, and in all those formulas that we did, we saw that in the end we were figuring out what the molar mass. In elevation of boiling point, in depression of freezing point, we were what, figuring out the MR or the molar mass. Now, you know that colligative property basically depends on what? Colligative property depends on the number of moles. So all the colligative properties that we were doing, they all depended on the number of moles and not the nature of the solute. So colligative properties depended on the number of moles and not the nature of solute, right? Now, you know that moles, now let's take an example. Let's take an example of, let's say KCl, right? So if you're taking 1 mole of KCl, okay, so if you're taking 1 mole of KCl, right? Now what happens is when you take 1 mole of KCl, it can dissociate. KCl, when added to water, it can dissociate, because obviously an ionic compound when added to water, it will dissociate into what? It will dissociate instantly into ion. So this will dissociate into K plus and Cl minus, right? As soon as you put this in water, it will give you, so you added 1 mole, and then what happens is basically that 1 mole splits into how many moles? 2 moles, right? So basically what you are doing is the mass that you will be calculating or the MR that you will be calculating, it will be incorrect. Let's see an example of KCl since we're at it. Basically what happens is that there's certain compounds which result in dissociation, certain compounds can also result in association, and we will just see when that happens, when dissociation or association happens, the number of moles change, and when number of moles change, the colligative properties change, right? So basically what you're doing is what you're calculating is kind of incorrect. Let's see KCl. You know KCl has a molar mass of 74.5. It's 74.5 grams per mole. Okay. So this is for KCl, right? 1 mole of KCl. Colligative property obviously does not see the nature of the solute. It only sees the number of moles, right? Now, if you have 74.5 gram per mole of KCl, now I know it is KCl because obviously I'm testing for it, right? Now what happens is, you know that let's do the change in boiling point. Let's do that of 1 mole of KCl. The colligative property, you know, delta TB is equals to Kb, which is the bulloscopic constant, times the molality, right? This right here is basically what? Number of moles of solute upon the solvent in kilograms, right? 1,000, right? Basically. So this right here is number of moles upon the solvent. Say, so now what you're doing is, let's say your Kb, I give you the value of Kb for KCl as 0.52, right? Now, so basically what you initially put was 1 mole of KCl. But what happens to KCl is that it's going to dissociate into K plus and Cl minus, right? So technically now you don't have 1 mole, but how many moles do we have? We will have, let's say it's 0.52 K is the Kb, and now we will have how many moles? We will have 2 moles, not 1 mole. 1 मोलल नहीं है, अब आपके पास कितना है? 2 मोलल. So your delta TB, let's say, comes out to be 1.04 K. That is your value of delta TB, right? Now, you know that delta TB basically, when we further wrote down the equation for the elevation, we said that delta TB is equals to, you know that the moles is, the molality is moles upon the solvent in 1,000 grams, right? 1,000 grams of solvent. And you know the moles is what? Mass upon MR, right? Can I say mass was MW2 and MR was N2, right? We did this whole expression in the previous class. So you know that TB is kind of equal to W2 upon M2. The TB that you calculated is kind of what, for 2 moles. It is not for 1 mole. The TB that we calculate is for 2 moles. Can I say I'm getting double of TB? Because I'm calculating it for 2 moles. And you know that the MR or the molar mass is inversely related to what? It is inversely related to TB. So if your TB has been doubled, so delta TB has been doubled. Why? Because I calculated it for 2 moles, right? I was expecting 1 mole, but 1 mole to gives off 2, right? And obviously your colligative properties do not know bhai ye K plus or Cl minus hai ya Kl hai. They will just see the number of particles which now have doubled. So the TB that you calculated was an overestimated value. By how much? By double the amount, right? And you know the delta TB and molar mass are inversely related. So if your TB has been doubled, can I say the M2 would half, would be like whatever value of M2 you calculate. If this is doubled, this will be halved. So the molar mass through this colligative property that you calculate comes out to be 37.25 gram, and you can prove it experimentally कि आपके पास तो ये आया, and do you see it's half the value of what it should have been. And why did that happen? Because यहाँ पे dissociation हो गई, right? So dissociation leads to what? The value of molar mass that you calculate comes out to be abnormal, because the dissociation results in double the amounts of moles. So the colligative property that you calculate is twice the amount that it should have been. Because the colligative property is twice the amount, because of that, the molar mass will be halved. Why? Because they're inversely related. So this type of property is, this type of molar mass calculation is what we call abnormal molar mass. Do you see it's not normal? It should have been what? 74.5, but it is abnormal molar mass. And this is due to dissociation, right? It can also be due to association. Now, obviously, we cannot predict the dissociation and association before the reaction, right? This obviously we figured out because we knew this was happening. We knew it was KCl. And when we used the colligative property to calculate the molar mass, it turned out to be half its actual amount. It was abnormal. So this was due to dissociation, we figured. Now there could also be association. That means maybe 2 particles or 2 molecules, they come together to give you 1. This happens in, an example of association would be 2 moles of ethanoic acid. In benzene, they will dimerize, right? They will become what? 2 moles of ethanoic acid, they will become what? 1 mole. 2 of them will combine to give you what? CH3COOH twice. They dimerize in benzene, right? In benzene, they dimerize. And this is what they look like. So you have CH3COO. So basically through hydrogen bonds, they make a dimer. They become something like this. So they make a dimer like this. These are your hydrogen bonds. Now, do you see that 2 molecules or 2 moles give you 1 mole? So the colligative property which you will be calculating for this, if I'm supposed to be calculating TB, delta TB. So now technically my delta TB would not be for, if I were expecting, can I say it's halved now? If this was 1, this would be 0.5, right? So what I'm doing here now, my delta TB would be for 0.5 mole, right? So my delta TB kind of now has been halved because आपके पास association हो गई, so the number of moles have reduced to half the actual amount. So if my delta TB has halved in this situation, what will happen to my M2 or the molar mass? My molar mass calculated would be doubled. This again is what? Abnormal molar mass, right? So due to association or dissociation, sometimes we tend to calculate what? Abnormal molar masses. And obviously you cannot predict that beforehand, because like some electrolytes can be strong, some can be weak, right? Like strong electrolytes, they will completely dissociate. Weak electrolytes will undergo partial dissociation. I mean, let's say, okay, like we took KCl. KCl was a strong electrolyte. It dissociates fully, right? And it's very easy to kind of predict that, okay, fine, if it's dissociating fully, one will be giving us two. But what if it's something which is a weak electrolyte? A weak electrolyte will not dissociate completely. Also, it will dissociate partially. I mean, it won't. So a strong electrolyte, you know, okay, this one guy will be giving 2 moles. So what I've done is I have basically overestimated my colligative property, and my MR or the molar mass that I'm going to calculate will be half its actual amount. But if you have a weak electrolyte will not dissociate at all. It will undergo what? Partial dissociation. Ab how can you really predict कि कितना dissociate किया होगा? How can you how can you figure out the percentage dissociation? So it becomes like, and you can't predict that beforehand, because it is not necessary that all of it will dissociate. It is not necessary that none of it will dissociate. There will be partial dissociation or association for that matter, as we just saw, right? So in 1880, Van Hoff basically found a solution to this entire thing. And he called it the Van Hoff factor, the whole factor, because he kind of figured it out, and he called it what? The Van Hoff factor, which was denoted with a I, a small I. Okay, so the Van Hoff factor was basically kind of like a rectification in this entire abnormal calculation. You can rectify this abnormal calculation through the Van Hoff factor. Okay, and every colligative property that you calculate, you multiply this Van Hoff factor with that colligative property as to rectify the error you may be making in the calculation of molar mass. So what is the Van Hoff factor? Basically, you multiply this Van Hoff factor, and it's not one value. It's not a constant value which applies to everything. No. So this is variable. Obviously, it is specific to each compound. So you multiply the Van Hoff factor with the colligative property so as to negate or nullify the effect of any error you are making in calculation of the molar mass. So you multiply this factor with the colligative property to rectify the error in calculation of molar mass, or M2, right? And how do you find out I? How do you calculate I? So there are multiple ways to figure out I. You can find I through the normal molar mass, the value of the normal molar mass upon the abnormal molar mass. For example, we were doing KCl, right? So you could have done 74.5, which was the normal, upon the abnormal that you calculated, which was 37.25. And when you do that, you get a value of 2. And you can see that it is 2 because aapke paas ek KCl is giving you 2 moles, right? So you can do normal molar mass upon abnormal molar mass. Now, you know that the colligative property, whatever it is inversely related to, like we just saw, delta TB is equals to W2 upon M2. Do you see? Molar mass के साथ inverse relation है of colligative property. So first way you can calculate I is in terms of molar mass. The second way you can calculate I is in terms of the colligative property itself. Okay, and since obviously they're inversely related, so this formula, which was for molar mass, will be flipped for the colligative property, right? Because you know that the colligative property, can I say colligative property is inversely related to molar mass? Sahi hai? So this, now if you want to express I in terms of colligative property, what will you do? It will be I is equals to observed colligative property upon the calculated colligative property. So you can express it in terms of colligative property, you can express it in terms of molar mass, you can also express it in terms of number of moles. So it can also be expressed in terms of moles, which will be total number of moles of particles after dissociation or association over the number of moles before, total number of moles or particles before association or dissociation. For example, if you're taking the example of KCl, the total number of moles after dissociation were 2 and before association were 1. So the colligative property, the I Van Hoff factor for KCl is 2. If you take the molar masses, again, we know that it would be 74.5 upon 37.25. Again, the factor would be 2. So basically, you can express Van Hoff factor in terms of moles, in terms of colligative properties, and in terms of what? The molar mass, right? So you can multiply. Now you have to use this I or the Van Hoff factor for all the colligative properties. And what you will do is that you will just put this Van Hoff factor of each I in what? Their respective colligative property formula. Right? For example, if your delta TB initially we were doing is equals to a buloscopic constant times the molality, now you will basically say times I, right? Tf is equals to the gyroscopic constant Kfm times I, right? Osmotic pressure. So osmotic pressure was what? Molarity, right? Molarity times the gas constant times the temperature times I, right? Relative lowering of vapor pressure. Again, all the colligative properties, you will just equate I to that so as to rectify any abnormal calculation you may be making, because we're not aware of the dissociation or association. So relative lowering of vapor pressure will be what? P1 naught minus P1 upon P1 naught, which will be that's the relative lowering of vapor pressure, which is equal to N2 upon N1 times I. So basically all the formulae that you have previously done, you will just put I with all of them as to what? As to what? Rectify the error in calculation of the molar mass. Now you know that the strong electrolytes, they dissociate fully. So the strong electrolytes, since they dissociate fully, their Van Hoff factor, like if for example, you know KCl, right? So strong electrolytes, since they dissociate fully, their Van Hoff factor is usually the integer of the ions they make, or the number of ions. It's an integer value and it's basically the number of ions they make. For example, KCl, it will make 2 ions, so the Van Hoff factor will be 2. NaCl will make 2 ions, strong electrolyte, Van Hoff factor will be 2. MgSO4, Van Hoff factor will be 2, right? K2SO4, K2SO4, the Van Hoff factor will be 3, right? Whereas C6H12O6, it's a molecule, it will not dissociate, right? So the Van Hoff factor, it will exist as 1, so the Van Hoff factor will be 1. Right? So basically it's a table, and I can send you the picture of the table where certain compounds and their Van Hoff factor values are written. So just as to eliminate the chance of error that you make in the calculation of MR or the molar mass, you just multiply all the colligative properties to avoid abnormal molar mass calculations. And that's why you multiply all of these with what? The Van Hoff factor. and this will basically vary for each, and you don't have to remember all of them, but like a few like strong electrolytes, and you should understand that molecules will not dissociate, hence their Van Hoff factor will be 1. They will not dissociate or split into any ions, so hence their Van Hoff factor will be 1, whereas the strong electrolytes, their Van Hoff factor will be equal to the number of ions they make, right? So you can easily deduce that. There are a few values of other compounds and their Van Hoff factors, and I can just push that forward on our WhatsApp group. Okay, so this is that, and this was it. This was the only thing which was left from what do you call solutions and electrolytes. And now we're gonna start with reaction kinetics. Okay, so I'm just gonna end this video right here.